Hello. So in this video, I'm going to talk about topic 2.4, connecting differentiability and continuity. Okay, so we've started to kind of hear this word differentiable. Ultimately, the term differentiable just means that you can take the derivative of a function. Okay, at that point. So if a function is differentiable, then ultimately the derivative does exist, or the slope of the tangent line does exist. I can draw a tangent line at that point. So again, differentiability really just means that the derivative does exist, okay? And if you kind of read through the top here, um, a function f of x is considered differentiable f prime if f prime is continuous for all points in the domain f of x. So, if I call a function differentiable, that implies continuity, right? So that's kind of the two essential statements that I have here. The first one, if I call a function differentiable, you can assume or you can make the connection that a function is continuous, all right? However, if I tell you that a function is continuous, we cannot assume that it necessarily is differentiable. And that's kind of the focus of this lesson. Okay. Continuity does not imply differentiability. All right. Just because the point exists doesn't mean the derivative exists. So we have this term called local linearity and a graph below it that kind of outlines what local linearity and differentiability are. If you take a look at these two graphs, right? We have a point here, and I can draw a tangent to kind of mimic the slope at that point. Okay, a tangent does exist, and ultimately, if you were to take technology or your calculator and zoom in, zoom in, zoom in on that point, it would appear to be linear, and that's kind of what that blue bubble is trying to show. If you were to zoom in, zoom in, zoom in, you would get kind of a picture of what that tangent line looks like. Okay. Now, the absolute value of x that's right next to it has this little corner here. Okay, it has this sharp turn. It's not a smooth curve, and because of that, no matter how many times you zoom in, it will never appear to be linear, and therefore it does not have local linearity. Okay, so the idea here is that anytime you have a sharp turn at a point, we'll go into a couple different ways in which that can happen. But those are places where local linearity does not exist, and those are places where your function will not be differentiable. Okay. Now, we have two criteria for a derivative to exist at a point. Okay. The first one is it must be continuous. So that's what we're just kind of talking about. So your function must be continuous at, let's say, x equals a. All right. Now the second criteria is in this blue bubble here, and I want you to be able to read the mathematics. All right. So if you notice, and it's hard to see my apostrophe here, but there is a prime, f prime, and this is also f prime. Okay. So it says the limit as x approaches a from the left of f prime of x is equal to the limit as x approaches a to the right of f prime of x. And ultimately, those are going to equal the same constant. Okay. Now, what does this mean? In mathematical language, if I were to change this into verbal, the slope from the left has to equal the slope from the right, right? F prime finds slope, or the instantaneous rate of change. So the instantaneous rate of change from the left has to equal the instantaneous rate of change from the right, okay? Now, so if you have a function that's continuous and satisfies this limit statement, then we can say that the tangent line does exist, or that this function is differentiable, okay? So we're going to take a look at a few graphs and a few examples that are and are not differentiable, okay? So these four there's four big obstacles that we need to watch out when we're talking about differentiability. The first one is the one that we just kind of talked about, is a corner, all right? Now, if you can see here, to the left side of that corner, all right, so I'm in the upper left box here. The left side of this corner is a negative constant slope. And then it hits this point and it goes positive. So the slope from the left and the slope from the right are not going to be the same. You have a constant negative slope on the left-hand side. You have a constant slope of a positive on the right-hand side. And those will never approach the same value. So therefore, it's not differentiable. The second one is very similar to a corner. It's called a cusp. So f of x equals x to the 2/3. This is an example of a function with a cusp. And it like a corner, you can see here, it's got a very sharp turn in it. And when you have that sharp turn, we will not be differentiable. Again, the slope from the left does not equal the slope from the right. All right. Now, vertical tangents are interesting because the slope from the left and right do approach the same value, and it is continuous. However, at this point, we are going to have a tangent that's vertical. And all vertical lines have an undefined slope. Okay? So if your slope is undefined, and your derivative finds slope, essentially you're just saying that your derivative is undefined or your derivative does not exist, right? So if you have a vertical line with an undefined slope, you're saying that the derivative at that point is also undefined. It would be a point that's not differentiable, okay? So, and then last but not least, the first criteria of differentiability, or the first criteria for a derivative to exist, is it has to be continuous. So anytime you have a discontinuity, your derivative would not exist. Okay, so there's a few graphs down here. State whether the function is continuous, differentiable, both, or neither. Okay, so what I want you to see here, okay, I'm going to say that this is at some x value a. All right, this function is going to be continuous from negative infinity to a, and then a to infinity. Okay, now because there is a discontinuity at a, it can't be differentiable there. So my interval of differentiability is also going to be negative infinity to a to infinity. Okay, so in this case, at a, because the point doesn't exist, we can't have a derivative there. But also, to go a step further, there's a corner there, right? There's a sharp turn. We can't have that. We only deal with smooth curves when we deal with derivatives. So if you take a look at b, I'm going to say it's continuous from negative infinity to infinity this time, because there is no hole. However, it's still differentiable. Let's say this is still at a, from negative infinity to a to infinity. So the point does exist, but because there's a corner at that point, it's not differentiable. The derivative does not exist at that point. Okay? If you look at part C, I could say that this is continuous from negative infinity to positive infinity. And it's differentiable because the whole thing is a smooth curve. There are no corners, cusps, vertical tangents. So I can say that this is differentiable from negative infinity to infinity as well. Okay. Last but not least, I have it's continuous. We're going to say that this is at a, from negative infinity to a, union a to infinity. And then we're going to say that it's differentiable over that same interval. Okay. Again, we would have to exclude A from our interval of differentiability, just because you can't be differentiable if it's not continuous. So if it got excluded from our interval of continuity, it cannot be part of our interval for differentiability. So again, anywhere there's corners, cusps, vertical tangents. So here's a picture of what those look like. All right. Any of those points cannot be differentiable. In the future topics, we're going to talk about how to explore that algebraically. All right. But visually, and also I want you to understand for future topics this definition, for differentiability, the slope from the left has to equal the slope from the right, in order for it to be differentiable, and it must be continuous. That's very, very important. Okay. So this was topic 2.4. Hopefully it helped.